All right, folks, here's another helpful hint. Last but not least, this is for Chapter 11, Problem 66. This is from assignment 2. Notice the 3 dots once again, and this is legitimately a tough problem, or a tougher problem, but it starts out okay. We have a small 50-gram block slides down a frictionless surface through a height h20 centimeters, and then sticks to a uniform rod of mass 100 grams and length 40 centimeters. The rod pivots about O through angle theta before momentarily stopping. Find theta. All right. Well, first you're gonna apply conservation of energy to determine the speed of the block just before it hits and sticks to the end of the rod. So just using energy, PE, or in this case, potential energy at state 1 is going to equal the kinetic energy at state 2. And you know the drill. The speed just before it hits is going to be the square root of 2 GH. Okay. Now that's out of the way. The second part of this problem, you're going to apply conservation of angular momentum to determine the final angular velocity after the collision. But you can use that as your initial kinetic energy when the block becomes one with the rod. Okay. So you've done this several times in the previous problem, but the angular momentum of the block just before it touches the end of that stick is going to equal to the angular momentum after the collision takes place. So big L, again, stands for rigid body, but with the mass stuck to it. Okay. Now, I'm not going to show you. I'm not going to have you put all that stuff in there. I think you can figure that out. But I will tell you the expected final speed that you're going to need in order to carry the problem through. Reasonable answer, and it's approximately 2.97 radians per second. So there's the answer in that regard. All right. Now, let's perform our energy mass balance. So what we're going to do is assume that the kinetic energy that the block and the rod had is then going to go to another state of energy, which is energy of position, when the block and the rod momentarily stops, for which we're going to determine the angle. That being said, let's identify energy at state 1. That's when the block, just after it collides, okay, we're going to call that kinetic energy, initial. And then the energy is going to transform into gravitation potential. So let's call that UG, I guess 2, or final for that matter. You get my subscript. So the first part, after the block hits and sticks to the rod, we're going to have the energy at that moment of 1/2 I omega squared. Okay. Now, energy position. Well, there's 2 things to consider. Hopefully I'll make this clear. I'm going to go to the diagram. I want you to focus your energy on the center of the mass of the rod. Okay, at the center of the rod, but that's the center of the mass. And then let's focus our energy on the mass. So this technically you can divide these 2 things separately in terms of their energies that they represent. The rod, about its center of mass, and then the mass at the end of the rod. So this is what it looks like. We're going to have the, whoops, wrong color. Let me back up the truck here. And so that kinetic energy of the monolith, rod, and the block is going to equal the change in potential energy. We're going to call it mgh. Okay, let's call it block plus the mgh of the rod. Okay. Now we're taking the center of mass into account. So if you think about this, I'm going to draw. Okay, there's the rod with the block stuck on it. Okay, this is where it is, fully length. All right. So there's the h of the block, And then here's the H associated with the center of mass of the rod. So we're going to have two terms here. Now, what is that H in terms of theta? I think you should have this memorized by now. But in terms of the block, all the way out along that L, and it's all the way along the length of that rod. Okay, so the block's going to be mg(L) quantity 1 minus cosine theta. Okay, that should be familiar. Then we're going to add to that mg, this time, the center mass of the rod. So that center is located half L. So that's going to be L over 2 times the quantity 1 minus cosine theta. All right. Now, I'm going to leave it at that and expect you to carry the rest of it through. So I'm going to take a peek at the solution and see. Yeah, I'm going to rely on your good algebra. So 1/2 I omega squared. Okay, that was the final omega from the previous. And then this rotational inertia is the sum of the rod plus the block after it sticks. But do the rest of the math on your own.